Equilibrium constant. At equilibrium, the concentration of the light and the concentration of the dark are at a fixed ratio, and this fixed ratio we call an equilibrium constant. At the equilibrium, concentration of the reactant and the product are at a fixed ratio. That's called equilibrium constant. Now we're going to examine further detail. In a equation, this ratio is 1, 2, become 3 and 4. Reactant become the product and it's a reverse arrow. Now let's put it into the equilibrium constant formula. The formula, you will realize one thing different. The product, you see the 3 become power 3. 4 become power 4. The reactant, 1 is power 1. 2 is the power 2. And you realize the product is on the top. Reactant is at the bottom. Please remember this rule. And this rule is a hidden rule. And I'm going to show further example to demonstrate this K constant rule important. Now I'm going to demonstrate this equilibrium constant by field experiment. I put the product on top, the reactant at bottom. And now let's start the first experiment. On the top, first I'm going to put in a lot of product. And the reactant, I will start with no reactant. According to the equilibrium rule, those products on top will slowly decrease until it reach equilibrium. The bottom one. The reactants will slowly increase until it reach to an equilibrium. Now let's do another experiment. Now this time, the product, I don't start with plenty. I start from none. I give no product. But the reactant, instead of none, I put plenty of reactant this time. And you see, watch the product. Product will slowly climbing up until it reach equilibrium. And the reactant will slowly going down until it reach equilibrium too. And now let's look onto the number. If you look onto the concentration number, this number doesn't quite match with the second experiment number, nor the reactant. Then you'll be a bit disappointed that you thought, well, it should be the same concentration, but that's not. But if I put it under this equation, and this hidden rule will show, if I put the product over the reactant, remember product is the power 2, over the reactant, and now I do the same on the second equation, product over the reactant, you realize this hidden rule of K constant will show they both will equal to the 0.2, 0.21. If you don't believe it, let's do one more to prove it. Now, I'm going to start the product reactant. They both exactly half product, half reactant. And see what happened. Remember, equilibrium doesn't mean half. They may be 1/3 product, 2/3 reactant, don't know. But you will see the top one will slowly going up further. The bottom one will slowly going down a little bit more until it reached to a new equilibrium. And now I'm going to test this number. Product over the reactant rule. And now you see on these three numbers, they all equal to 0.21. So it proves one point. Regardless how you start the concentration, you start with plentiful of A or plentiful of B, it doesn't matter. They all will come to the same constant value. And this constant value, when you apply it into this equation, it will reveal. So on the equation, if you see any equation with an equilibrium sign, you can all apply this product over the reactant rule. And now let's see. Product over the reactant will give you a constant number. The second one, the third one, the fourth one. Well, wait a second. How come this one, should it be product over reactant? Look, this is solid. HgCl is solid. Solid does not apply to equilibrium, so it's not counting. So you put HgCl. This one too, CO2. How come CO2? Again, solid. It doesn't apply to equilibrium. Equilibrium is only for aqueous and gas. And now, after we put product over the reactant at equilibrium, now they give you quite a few of a constant number. And what does this constant number mean? You realize certain constant number, the number value are quite big. Certain number, the number value are quite small. What does that mean? If the number are quite big, that must be the product is big over the small reactant. So this will give you a larger value. Means, okay, if the value is small, that means the product must be small, reactant must be big, so that you come to the small value. When the time it gives you a big value, that means you're going to have a lot of product. When the time it gives you a small value, that means you will have a lot of reactant. Keep in mind, nothing is absolute. As you see in this equation, HgCl is partially soluble as Ag and Cl. You might remember HgCl are not soluble. They will precipitate. Then your question is, are they 100% precipitate? No, they will be 99.999%. And how much would it be? So you will say, are they still partially soluble? How much partially soluble is partially? Now this value will tell you. And you know by looking onto this value, this is very, very much towards reactant. So you will be basically, you get most of the most as HgCl solid. So this equilibrium constant, it is important. When you have an equation and if you at the equilibrium and it doesn't give you the constant, and this equation is pretty useless because it didn't tell you how much will it give product. Is it a little bit or a lot? And you cannot tell. So you must have a K value to indicate in this equation, how much would be the product or how much would going to be the reactant? How much is the forward or reverse reaction? So this K value is give you a good indication how much is towards one side or the other. Now let's look on to the equilibrium constant with Le Chatelier principle. Under the equilibrium constant rule, product over the reactant, as we just mentioned, if you have an equation of equilibrium, you must write the K. You don't write the K, we don't know how much product or how much reactant or which ones go more favored than the other. So we must have the K value. Okay, we put the K value. How about Le Chatelier principle? What's Le Chatelier principle? Let's refresh. If you have an outside factor imposed onto the system, like temperature, pressure, product reactant change, the system will shift to respond to the change. Then you may ask, hey, does this constant still the same as? Look, if I put more reactant onto the system, and according to the rule, it should shift more towards the product side to increase more product. So does that mean the equilibrium constant will change? Now I address this matter, and the answer is the K will not change by this Le Chatelier principle. It will remain constant, no change, constant. Now I'm going to prove by experiment to you. Let's see an experiment. In this equation, I have a K value, which comes from the concentration at equilibrium. I put product over the reactant, give me the K value. Now I'm going to do the second experiment. I have exactly the same equation, but this time I disturb it by I add more hydrogen gas into the system. So the equilibrium will shift now until they reach to a new equilibrium. I measure the concentration. When I put under the K equation rule, it gives me the same value. So this is to prove my point that the outside factor under the Le Chatelier principle, it does shift the equilibrium, but the K constant does not change. How about temperature? Temperature have a funny rule. At 100 degrees, this is the value of K. If I put on 0 degrees, the K value is totally changed. So the conclusion is equilibrium constant. When change in reactant or change in product or change in pressure, it will not affect equilibrium. But change in temperature, it will be a new equilibrium. So it will change by temperature. So let's compare Le Chatelier principle. As you see, the product reactant will shift. Temperature shift. Pressure favor small or big number. Catalyst no effect. Now look onto the K. No effect, no effect. Only effect is the temperature. Otherwise, K constant is constant. No change. It would not change by product, reactant, pressure, or catalyst. Only thing can change the constant is the temperature. Reaction quotient. On other condition, this ratio of product and reactant is called reactant quotient, as means they are not yet reached equilibrium. The equation will be the same, product over reactant, same as the K that you do calculation. Now I demonstrate to you. Imagine if the K value when you reach the equilibrium, product over reactant is 50. You have your experiment and the value give you called the Q quotient, which is 80. That means they are not matched. Then the Q is not K. So that means in this experiment, your product will slowly further decrease, reactant will slowly increase until it reaches K. If the Q value is smaller than K, that means it's not reached K. So slowly it will change again. Product will slowly climbing up. Reactant will slowly going down until it reach to the K value. Now let's do calculation to prove. Example 1. Equation. The K value is 57. Pay attention. The K value is given to you as 57. And you do the experiment. You find that the concentration value, this is what you find. So you put it onto the equation as Q, product over reactant, give you 81. Is the system at equilibrium yet? You know the Q value is bigger than K. That means they are not at equilibrium. So what will happen? Product will decrease, reactant will increase until it reaches equilibrium. Do one more. I use same equation. If this time your experiment turn out to be of this value, you put onto the Q equation, product over reactant, give you 41. Is the system reach equilibrium? The Q is smaller than K. Means the product will increase more, reactant will decrease more until it reaches to equilibrium, the K value. Initially, they have 2 moles of sulfur and 2 moles of oxygen. At equilibrium, it gives you 0.15 mole of sulfur dioxide remain. The other is unknown. Look at this equation. What does this give you? What does this information give you? The information say when initially they give you, finally they only give you one value. The other value they didn't give you. So how you going to put this information into the K equation? Too much unknown. You can't do it. So now we're going to talk a way to solve this question with some unknown product. Here the equation. First, in the beginning, the reactant is those unreacted. The product is the reacted, already reacted. Let's do the ratio 2, 1, 1. Now write down initial change equilibrium, ICE, ICE. This is called the ICE rule. So ICE, you can see ICE. Then they say initially you have 2 mole. How much initially will you have for product? Think. In the beginning, will you have any product? None. You won't have any product. Then, at equilibrium, what did you get? I got 0.150 mole. Did you know the other two factors? No. Now, using this ICE rule to work the way for the change. The change always, the unreacted will slowly decreasing. I put minus. Reacted, those in the beginning will slowly increasing. I put add. Please remember. I work the way up. So, the difference between initial minus the equilibrium. The initial number minus equilibrium give me this value. Now you work out the other value. Remember the cross multiply rule. You times 1 divide 2, like early I teach you. Times cross multiply times 1 divide the top. So we give you this value. The second one, the same rule. You times 2 divide the top. You times 2 divide the top. Those cross multiply we do on the early equation. So now you have all the change value. Now we do the sum. Here you get 2 minus 0.925. Here 0 plus 1.85. So now you have all the equilibrium value that they short of. Now you can put it onto the equation of K. Now you can work out the answer. Student, Please practice a few times. In this equation, the trick is you will have initially number you know. But when you reach equilibrium, they only give you one of the factor. The other are unknown. And you have to find the other unknown to put onto the K equation. So you're using this ICE rule. First, the ratio 2:1:1. Number 2, initial you have no product. Number 3, work the way back. Minus, minus, plus. How to get the x value? Cross multiply and divide the top. Cross multiply, divide the top to get the value. Then you can work these things up.